Now, to prove this general statement by mathematical induction, we say let P of n represent the statement. Now, the first step is called the base case or the basis. Here we prove that the statement is true for n is equal to 1. So prove that P of 1 is true. To do this, we take the left hand side, substitute 1. So we have 1 times 2 raised to 0 divided by 2 times 3 here. So we have 1 over 6. We substitute 1 for the right hand side and check whether they are the same. For the right hand side, we have 2 divided by 3 minus half, which is also 1 over 6. Since the right hand side is equal to the left hand side, we say that the statement is true for n is equal to 1. The second stage is called the assumption. Here we assume the statement is true for n is equal to k. So assume P of k is true. So here we just write that for P of k now, we have sigma from j equals to 1 up to k of j 2 raised to j minus 1 over j plus 1 to j plus 2 is equal to 2 raised to k divided by k plus 2 minus half. So the third step now, we call the induction step. So in this step, we assume the statement, we prove. We now prove that the statement is true for n is equal to k plus 1. So prove that the statement is true for so here now we want to prove that P of n is true for k plus 1. So let us take the right hand side. We substitute k, then we add it to the left hand side where we substitute k plus 1. So we have now our right hand side 2 to the power of k, or 2 to the k power, divided by k plus 2 minus 1 over 2, then plus the right hand side now, the left hand side. So we have k plus 1 times 2 raised to k plus 1 minus 1 divided by k plus 2 to k plus 3. So we can now write 2 raised to k over k plus 2 now. So we can say plus k plus 1 now times 2 to the kth power divided by k plus 2 into k plus 3 minus half, which you can also write as 2 to the kth power into k plus 3 plus 2 to the kth power into k plus 1 divided by k plus 2 into k plus 3. So here we use k plus 2 times k plus 3 as the LCM minus half, and that gives us 2 to the kth power into 2k plus 4 when we factorize there, divided by k plus 2 into k plus 3 minus half. So you can now write 2 to the k power times 2 into k plus 2. This k plus 2 divided by k plus 2 into k plus 3 minus 1 over 2. So k plus 2 we cancel out, so we have 2 raised to k plus 1, first law of indices, divided by k plus 3 minus half. So if you like now, you can stop here, or you can write it as 2 raised to k plus 1 divided by k plus 2 plus 1. You can put this in parentheses, then cover with a bracket, minus half. So here we have shown that the statement is true for n is equal to k. So the last step now, so here we have shown that the statement is true for k plus 1. So the last step is the conclusion. Our conclusion now is that P of n is true for all positive integers. So it means that P of n is true for all positive integers. This sign here means for all. So that is how to prove by mathematical induction.